on solving directional dynamic games for all Markov-perfect equilibria. So we're going to look at a particular class of games that has a directional state space. So loosely speaking, this means that when states are making transitions, they're only really moving in one direction. Okay, so one example would be like human capital accumulation without any depreciation of human capital. That would only go up, okay, never go down. Okay, like bargaining over a stochastically shrinking pie. That's a pie that would never grow, but only shrink while players, they are fighting for it. Okay, so these are like examples of directional games. Anyway, I'm going to be much more specific about that. Okay, but this is the class of games that we are looking for. Okay, and trying to work on. Now, so the next couple of minutes or hours is going to be about a line of research I've done with John Rust and Fedor Iskhakov on solutions of and estimation of dynamic games. So I'm going to start with some of the results from a paper that came out in the International Economic Review in 2018 about the dynamics of Bertrand price competition with cost-reducing investments. So this is like a theoretical model of leapfrogging investments by duopolies who are competing with each other in a Bertrand price competition way. Okay, and so this is like a theory paper. And we're going to use this model as a workhorse to test both an estimation approach that we will touch on at the end, and then a solution, a full solution approach for solving this class of games that we call directional dynamic games. Okay, so there's a second paper that came out in ReStud in 2016 called Recursive Lexicographical Search, Finding All Markov-Perfect Equilibria of Finite State Directional Dynamic Games. And so this is a full solution algorithm that allows us to not only find one equilibrium, but actually guarantees to find all equilibria for this particular class of games. Okay, so given this full solution method, we can embed this in a nested maximum likelihood estimator. You know, it's similar to the nested fixed point algorithm, but where the inner loop, or you need to solve all Markov-perfect equilibria, is done by this recursive lexicographical search algorithm that we develop in this paper here. Okay, so I'm going to talk about that later. Okay, we do a bunch of things with this. It's robust to multiplicity of Markov-perfect equilibria, and we can relax the single equilibrium assumption in the data single equilibrium in the data assumption that's frequently used in the literature. Okay, in a relatively straightforward way. Anyway, so this is kind of the background for this lecture. Okay, so I'm going to start with the application. Okay, so it dates back to this is like empirically motivated theory in some sense. It's about a collusion case that John Rust was participating in as an economic expert in the in an Australian market for cardboard. Okay, so or corrugated fiber packaging products. Okay, and there was a collusion case between two firms, Amcor and VC. So I'm going to start with introducing that, and then talk about the Bertrand price competition game that they used to calculate the counterfactual but-for prices and the resulting damage. Subsequent the collusion, and then after presenting the model, I'll talk about how to actually try to solve it using this recursive combination of state recursion and recursive lexicographical search. Okay, so I'll do that, and then while I'm doing that, I'm going to define what directional dynamic games actually are, more rigorously. And then with this full solution approach of RLS, I'll present some of the results from the paper where with the theory, it's really a theory paper where we illustrate some of the theorems with simulations from the model, and these are based on a full solution with solving for all the Markov-perfect equilibria. And then after that, I'm gonna at the end, and probably in a separate lecture, talk about structural estimation of directional dynamic games with this nested RLS method, or NRLS as we'll call it. just brief. Okay, so here's a kind of an overview of the results in this paper, the theory paper about the leapfrogging model. So here we really extend the static textbook model of Bertrand price competition by allowing duopolies to undertake cost-reducing investments in discrete time. So, in the Bertrand price competition model, if the firms are competing on prices, really the Bertrand price is going to be equal to the marginal cost of the high-cost producer. So that's kind of begging the question from the point of view of the two firms. Why shouldn't I do anything to try to reduce my marginal cost so I can get some temporary leadership over the other firm? And that's all about what this model is really about. So here in this model, in this world where the firms are competing, this potential technological progress, which is stochastic and exogenous. Okay, so state-of-the-art production technology, or the marginal cost you can produce it, if you buy the technology, is reducing over time. And then each firm, they have a binary decision to acquire the state-of-the-art production technology. So you would say this is probably possibly the simplest possible extension you can make to this classic static model of Bertrand price competition. And yet, surprisingly little is actually known about Bertrand price competition in the presence of production cost uncertainty, especially in the dynamic setting. And you would be surprised to see what a huge plethora of equilibria, or multiplicity of equilibria that you find in this model once you make that slight dynamic extension. We show also, using the RLS algorithm developed in the ReStud paper, how to compute all the Markov perfect equilibria of this game, and show that this dynamic model of Bertrand price competition has a really surprisingly rich, complex, and even counterintuitive equilibrium outcomes that would have been really hard to predict without actually solving for the game. Okay, so let's go back to Australia. This is a picture of the beach where two executives from two firms, cardboard producing firms, they met on the beach, and so there was collusion on the beach, if you will, okay? Because they met, they were like fiercely competitors, and these two executives, Peter Brown, with the managing director of this firm called Amcor, and Harry Debney, the CEO from its competitive VC, well, they met on the beach and said, well, do you have a house here? Well, you need to live nearby. Why are we fighting over all these prices all the time? Why don't we, make an agreement, that we divide the market or something? And then they had like collusion on the beach, and they, they divided the market between them, and they'd say, okay, you're gonna have this part of the market, then you're gonna have this part of the market, and then they agreed on what the prices at the market should be, and there would not be enough competition, and that's illegal. Okay, so that's where that was discovered after the breakdown of the collusion, and there was no doubt about that. Everything was recorded at tape recorders. It was kind of it's kind of interesting to hear about. Anyway, let me just get to the point and talk about the cardboard market of Australia, because what John was called in to do was calculate what would the damage be after this collusion case. Okay, so the problem is we never really observed the counterfactual. What would have happened had these two firms, Amcor and VZ, not colluded in the market of cardboard? Okay, so what would the prices have been? Okay, and the difference between those prices, absence of the collusion, and with the collusions, that's a damage to the consumers, and in principle, or that's what they should pay to the damage to their customers, and they were picked in court to do so. Okay, so anyway, the Australian market for cardboard is essentially a duopoly. It's like there's only Amcor and VZ in this market. And then between 2000 and 2005, these two firms, VZ and Amcor, colluded in the market of cardboard to raise the prices of these CFP, or what it was, corrugated fiber products, or cardboard, really. Okay. And then, I'm sorry, this is like John's slides. So, so John was hired to estimate, and I'm Bertel, so I'm not. This is not John talking. Okay, so John was hired to estimate the damage caused by the collusion, which required predicting what the cardboard prices would have been in absence of the collusion. And his opinion was that the counterfactual but-for prices should have been those predicted by the Bertrand price competition in the short run. Okay. And we're going to make some arguments why this market is really like there's room for Bertrand price competition, but that was only in the short run. So what would the price should the price have been? Well, that would be the price of the marginal cost of the high cost producer. Okay, but then in the longer run, it would be Bertrand price competition with leapfrogging investments, where the two firms over the longer run would invest in newer technology to produce at lower marginal cost as a V for low cost leadership. So this like leapfrog investment, or first one firm invests, and then another firm invests, and then the other firm invests, and then by that the marginal cost is just going down, and therefore also the price is going to go down even further in the longer run. And of course the defense for Amcor and VC didn't really like that idea. Okay. Now here's really the smoking gun. So John, he was sent into these rooms with all these documents, and to figure out about these firms and how they're competing. And then he found this plan, this book about with this plan for this brand new paper mill. It's called B9. Okay, now Amcor was really like the high cost follower, and has been behind VC, was like the lean mean machine that was just driving the market for some time. And then they thought about actually leapfrogging VC by investing in this brand new paper mill that could really reduce the marginal cost of production. But guess what? After the collusion on the beach, B9 was abandoned. Okay, and so that was all canceled, and so by finding these plans that was just completely canceled right at the collusion time, this was like the smoking gun in court. Okay, and like a proof for these leapfrogging investments. Okay, so B9 is really an example of leapfrogging. The existing plans were like over 50 years old, and then this huge investment was like a $500 million investment would really bring in Amcor to be the new cost leader. Okay, and so here's some details about this machine, but it's really like high end paper product machinery that can really reduce the marginal cost of production. Okay, but then it was abandoned, and then after the collusion. So then another question is, why should this market be characterized by Bertrand price competition? See, but cardboard is really highly standardized product. It's used for so many things, basically boxes for fruit and all the stuff you buy online. It's all made out of the very similar material, cardboard. Okay, it's like gasoline for internet packaging. Okay, it's not like you care a lot whether this product is bought from Amcor or VC. Okay, so you care really mostly about the price. So the consumers of the cardboard are firms that are highly rational, interested in buying the inputs at the least possible cost. So these are like tenders that create these firms acquire these inputs via tenders that create really strong incentives, Bertrand-like price cutting. Okay, so in this case, they lack good data on aggregate demand for cardboard for facing Amcor and VC before and after the collusion, but they had good data on the marginal cost of the cost of production. Okay. And cardboard is really made on production lines with machinery that is well approximated by constant returns to scale with constant marginal cost. So you really got all the things you need for Bertrand price competition. Okay, so here's like a cardboard corrugator. You put paper in and glue in it, and then it wriggles the paper here in some way, fancy way, and then it comes cardboard out of the other end. Okay. Anyway, so then the question is, how should B9 be made? What are these type of? I mean, you would kind of, if you wanted to invest in new technology, it should be something that does something for you, like reducing the marginal cost of production, or increases capacity, or something like that. And so then the question is, how are you going to engage in that cost reducing investment? So for the case of Amcor and VC, it's really that they are doing minimal amount of research and development. Okay, there's really limited scope for new production innovations to replace cardboard. Okay, what they are doing is they're spending a considerable amounts of money on cost reducing investments, and they're not developing this machinery themselves. I mean, they like this cardboard corrugator. They are buying this latest technology or state-of-the-art technology and machinery for producing cardboard by other firms that are developing them. So it's not. I mean, I think they're buying them probably in Czechoslovakia or Germany, but they're certainly not developing this machinery themselves. Okay, so it's like technological progress with cost-reducing investments, but not in the shape of R&D with this uncertain payoff to it. They just go out and buy whatever is produced in these German or Czechoslovakian firms. Okay. So actually, when B9 came into place, it's Amcor led really to a price war, and so the prices fell dramatically, because now VC would be the high cost follower. It used to be the low cost leader, and then the price would competed now down to the new Patron price. Okay, and so. So after investing this B9, and well, it became reality that the prices would become much lower because of the leapfrogging. Okay, so that Amcor was now the low cost leader. Okay, now the economic experts defending Amcor and VC really totally dismiss the theory of Patron price competition and leapfrogging investment as being naive and totally out of touch with reality. Okay, they claim there's a huge body of research and empirical work in IO that supports the idea of tacit collusion. Okay, like for repeatedly interacting duopolies. So the idea is, Amcor and VC, even without talking to each other, they can think what the right colluding price would be, because they are tacitly colluding. Okay, so they claim that duopolies could achieve the collusive price via tacit collusion instead via illegal explicit collusion. Okay, and this would imply that the damages were exactly zero, because that's legal, right? Because if it's really tacit collusion, why would but if this is the case, and if tacit collusion is legal, why would Amcor and VC have any incentive to do any explicit collusion? So that didn't make a lot of sense. Okay, and actually, if you look at it, it's really hard to find empirical support for tacit collusion, both in experiments and in fieldwork and in laboratory experiments. And so there's several examples of that. I'm not going to spend too much time on it. Well, there's some work here on has suggested that you can have that the collusive price could be achieved through like price ceilings, which could serve as a focal point of give it like a search for a focal point effect. Okay, so but if you look at it in laboratory experiments, in here there's a there's a price ceiling of 28. But then the price ceiling is then increased. Well, the price increased, but then it gradually go back to the price of the marginal cost again, which is or the Bertrand price, which is 21. So this is like coming out of some laboratory experiments with experiment subjects, and this is like an example of experimental work. It's really hard to achieve the tacit collusive outcome. And here's a explicit. Here's some results from another paper with some experimental evidence on how communication is really necessary for collusion. So here you have different cases with different number of players. So here's a duopoly case where there's more scope for collusion if there's two, or the collusive price if there's two, but that in vast majority of the cases that required that they would have to talk to each other. Okay, whereas if there's more than a couple of players in the market, then it's just impossible to have any explicit any tacit collusion. Explicit communication is really necessary for collusion. So another example here, a thing that kind of that the defense would say to John, they were out of touch with reality with respect to suggesting this Bertrand price or Bertrand price competition in the short run with leapfrogging investments in the longer run. Say, why would if they're really Bertrand price competitors, why would they ever do any cost reducing investment? It's like logically impossible. Okay, because here's a line of thought. If suppose a pair of duopolies simultaneously invest in the state of the art of low cost reduction technology with marginal cost C, well, that's in principle possible because everybody can buy this machinery from Czechoslovakia, right? So if they do that in the same time, the Bertrand price competition following these investments would lead to the price equal to this new state-of-the-art marginal cost of production, so P equal to C, which would give essentially zero profits for each of the firms. So if each of the firms earns zero profits ex post, why would they have any incentive to invest ex ante? And see, now that's also a simplified way of thinking, okay? Because this is a dynamic problem, okay? And it's really this is an investment game that's anti-coordination game. So the firms could actually dynamically compete and coordinate their investments in equilibrium in order to avoid this bad simultaneous equilibrium, and that is actually possible. And now here I've posted as a question, but it's really possible. Think about it. If you can justify investment if it gives you temporary cost leadership. Okay, so there is of course a risk that the other firm is doing the investment at the same time as you, but you take that into account when you make that decision under uncertainty about what the other firm is doing. Okay, now. Riordan and Salant say it's not possible. There's a paper in a Journal of Industrial Organization by Riordan and Salant in 1994 that proves that in continuous time, if duopolis moves in alternating fashion and technology's progress is deterministic, so it's every period the technology is improving, then investment preemption is the only possible equilibrium outcome. And what is equilibrium in preemption? It is only one firm is investing in all the time periods. Okay, so it's aggressively investing in the newest the state of the art to preempt the other firm from doing any of the investment. But he's doing so aggressively in this overinvestment so much that it's all its profits and rents are completely dissipated, and in equilibrium both firms earn zero profits, and the prices is going to be at the high cost leader, and essentially all the surplus in the economy is wasted on on excessively overinvestment. So consumers are not getting anything out of this, and the firms are not getting anything out of it either. Okay, so this totally inefficient equilibrium. Now this thing here we talked about before, why should Bertrand price competitors undertake any cost-reducing investments? That seems like an investment paradox. Why would they do any investment if they get zero profits exposed? Why would they have any investment in incentives to invest ex ante? And that paradox we have a solution to in our paper. So what we do is we show that this endogenous coordination is actually possible in equilibrium. So the most prominent equilibrium is really the leapfrogging equilibrium, where the firms are making alternating investments and taking turns in being the cost leader. And so that would be what would be justified John's advice for how the damage should be computed in the Australian cardboard case. Okay. We also show that Riordan and Celan's conjecture is wrong. They conjectured that that leapfrogging, not preemption, is a generic outcome, and that it didn't really depend on the alternating move assumption, that it would also apply the simultaneous move context. That turns out not to be the case. It's actually really a knife-edge result. Okay, what we find too is that the price paths are piecewise flat and non-increasing, and price wars, they occur when the high-cost firm leapfrog its rival to become the low-cost leader. And so this was also what motivated why the damage in the long run should be much higher, because had B9 made it to the market, or had the Amcor invested in B9 and leapfrog VC earlier, then the prices would have been much lower for the consumers, and that would be used to calculate the damage. Okay? Should be used to calculate the damage. These price wars then leads to permanent price declines. So it's unlike the conventional interpretation of price wars, where you're making price wars as punishments for periodic breakdowns of tacit collusion. Okay, because they've invested in this B9, so marginal costs are lower, and then the new equilibrium price is also lower. Okay? And this is also what you observed, what happened after B9 was in fact a reality. Equilibria are generally inefficient due to overinvestments because of two features: duplicative investments and excessively frequent investments. Okay? But it is actually possible to achieve a fully efficient monopoly equilibrium in equilibrium. So actually, it's many things can happen in this model, and because there's a huge multiplicity of equilibrium. Okay, so that's that was the collusion case between Team Amcor and VC. And let's move on and talk about how to set up the Bertrand investment game that we would use to calculate the counterfactual prices in that market, and introduce the model and how to talk about how to solve for the Markov perfect equilibrium. Okay, we're going to use the solution concept Markov perfect equilibrium when we are solving for the equilibrium strategies and values. And then we move on to talk about the algorithm after this. Okay, so here's a game. So dynamic price competition. We got a stochastic dynamic game with two players, two competitors, Amcor and VC. So you got n equal to 2. There's no exit. There's no entry. Okay, so these firms are just in the market and then competing. The discrete time, you got infinite horizon. And each firm is maximizing expected discounted profits using a common discount factor beta, which is between 0 and 1. I think in our simulations it's around 0.95. Okay, so usual deal. Each firm has two choices in each period. They need to choose a price of the product, just like you would do in Bertrand price competition. And then whether or not to buy the state-of-the-art technology that is available at the market for cardboard machinery. Okay, so this state-of-the-art technology is just following some exogenous Markov process, and then you can choose whether or not you want to buy from this market. Okay, so the price composition is static Bertrand price composition in each period, and this is going to be a continuum of consumers who made static purchase decisions. Okay, so and we are we are considering the case of completely inelastic demand, in the sense that they are only choosing which firm to buy from. Okay, so very simple. There's no switching cost. You just buy from the low cost supplier. So with that, we move on and introduce these cost-reducing investments. Okay. By the way, the price is just going to be the standard Bertrand price, where the price is equal to the marginal cost of the high cost producer, if there's differences in the marginal cost of production. Okay, so how is this state-of-the-art production technology evolving? So we're going to start with some initial value C naught. Okay, so C, that's the marginal cost, state-of-the-art marginal cost. And then it has a lowest possible value that we're gonna, without loss of generality, just say is 0. Okay, so it started at C naught, and then it just moves down, and then the state-of-the-art production technology is must be between what it starts at and where it's at in it. It's a continuous state variable in principle. We discretize it. We can discretize it into endpoints. Okay. So yeah, so you can say the more discretization, the more continuously this process is developing. Okay, the process for the marginal cost of production is following this exogenous Markov process, and here's where the directionality come into play. It only improves. Okay, so this means that the state-of-the-art technology marginal cost of production is only going down. Okay, it can stay put with some probability, but it can never increase. Okay, so once they figure out in Czechoslovakia how to make these efficient machines, they're not going to throw that technology on the street. Okay, state of the art is only improving. Okay, so that makes it directional. Is really a directional state variable? Only moves in one direction. Okay, now then there's the deterministic or the investment choice by the firms. Okay, whether or not to adopt the current state of the art, so they can pay this investment cost that could potentially depend on what the state of the art production technology is, in order to obtain the new production facility that allows them to produce a new marginal cost. This is going to be a one period lag, construction time or time to build in the model. So the production facilities with lower marginal cost is only starting at the next period. Okay, so here's a state space and information structure. So the state of the game is the cost structure. So the marginal cost of firm 1, marginal cost of production of firm 1, marginal cost of production of firm 2, and then the state-of-the-art production technology. So in principle, 3 continuous state variables that we discretize. Okay, and then the state space in this discretized world is living in R3, or in a subset of R3. This pyramid, where C1 is always greater than the state or equal to the state-of-the-art production facility, because C, since that's only improving, how could you ever have a lower marginal cost than the state-of-the-art? Okay, so it must be greater than or equal to for both of the firms. Okay, these are these are common knowledge state variables, and also the actions are observable once they meet. Okay. Like we've had in the previous models, we have private information, and guess what? These are going to be either extreme value shocks to investing and not investing. Okay, so we call them epsilon, and then they are scaled by this variance term eta. Okay, or what we usually call sigma, but here they're called eta. Okay, these are either extreme value distributed and independent across choices, times, and firms, and this eta here is just a scaling parameter. And actually, we can start solving this in this framework here, which is eta equal to 0 for most of the cases. But we'll need that when we start estimating the model. We would need like an error term, so we will reintroduce it there again. I think also I'm using this ADA later on for some of the simulations from the theoretical model. All right, we're considering several timing of moves. Well, the prices are always made simultaneous. So simultaneous Bertrand price competition pricing decisions, and really it's the price is equal to the marginal. The equilibrium price is going to be equal to the marginal cost of the high cost producer, and so if you're the high cost follower that is following the low cost leader, you're going to get zero profits, right? Because the other firm is going to get the entire market. Okay, so only the firm with the cost advantage is going to get profits, and since there's like a unit mass of consumers, this is going to be equal to the cost difference. So what you can get here in this market is if the if you invest, you can potentially get the profits are equal to the the expected profits is going to be equal to the cost advantage if you're lucky enough to leapfrog your opponent. And you're going to get that for some time until you're going to be leapfrogged by the other opponent, and then you get zero profit. So your profit's going to alternate between what the cost advantage is and zero if you don't have a cost advantage. So we consider also, with respect to the investment decision, two versions regarding the investment decisions: simultaneous moves and alternating moves. So the simultaneous move, well, then the investment decisions are made simultaneously. But in the case of alternating moves, we have an additional state variable, which is like the right to move. A state variable, we call that M. The move is a state variable. It can be either one or two. Okay, so either firm one has the right to move, or firm two has the right to move. So when firm one, when M is equal to I, only firm I can make the cost reducing investments. So we're going to consider several ways of formulating. I mean, it could be, say, only firm one has the right to move. Always, it's like a monopoly. Monopoly in terms of in terms of that the right to move. Whereas you can also have a deterministic alternation where the turn of potential taking the action is deterministically alternating every time. So first firm one, then firm two, firm one, firm two. Or you can have like a random alternation, so that there is some stochastic Markov process that determines who has the right to move, which is kind of actually not really a bad approximation to reality. Sometimes it's just stochastic. Who really sees the who is seeing the opportunity that the new Czechoslovakia machine there's a good bargain for it at the market. Okay, or yeah. Okay, so that's the two cases we consider: simultaneous move and then various types of alternation of moves. Now, see, alternating, once you have this additional right to move state variable, that's actually a non-directional state variable that we have, because it is not only moving in one direction. It's not like if firm one has the right to move, then it can only move to firm two and never come back to firm one. That's not the case. That could be loops. These firms can alternate. So that's going against the idea, but we actually have ways to deal with that when this non-directionality is actually happening in an exogenous way. Okay, so here's the actions and behavior strategies. So you got the Bertrand pricing strategy, which is the max of the two cost. And then you got the probability of investment for firm I, okay? Capital I superscript for investment. And N for non-investment is just going to be 1 minus the other probability. Okay, so the probability of not to invest. And so the strategy profile is then the pair of Markovian strategies that consist of those two pricing functions and investment conditional choice probabilities, right? Conditional choice probabilities. And so of course these are functions of the state variables. Okay? These are functions of the state variables. And then pure strategies are also included here as a special case, because if you can invest with probability 1, that will be a pure strategy. But you can also be a mixed strategy where those probabilities of investment are somewhere in between 0 and 1. Okay, so here's the Markov perfect equilibrium. So the definition here of the Markov perfect equilibrium is, or of the Bertrand investment stochastic game, is a pair of strategy profiles for both of the firms, and a pair of value functions for both of those firms. Okay, the strategy profiles here, which would be pricing and investment probabilities, or investment policy functions, such that the Bellman equations that I'm going to show you are satisfied for each of the firms, so like Bellman optimality, and so that the strategy profiles constitute mutually best responses and assign positive probabilities to the actions in the set of maximizers of the Bellman equations. Okay, so this is just like we had last time. So you got the Bellman optimality and the Bayesian-Nash equilibrium conditions that constitute the mutual best responses. Okay, so here's the Bellman equation, and this is a case for the simultaneous move. So we got essentially 4 Bellman or discrete choice specific value functions for invest and not invest for both player 1 and player 2. Okay, and actually then there will be like 8 Bellman equations for in the alternating moves, because then there would be both a choice probability, or there will both be a choice-specific value function conditional on having the right to move and then not having the right to move. So twice as many expected choice-specific value functions. Okay. Anyway, so here's a value function. It's the max of the choice-specific values, including these idiosyncratic shocks to investments. And so if firm I is not investing, well, then it's going to be getting the revenue in wherever state there are. So C1 and C2. So if you're like a cost leader, you're going to get the cost advantage profits. If you're a cost follower, well, you're going to get nothing. Okay, and then plus the expected value of being in the same state in the next period. Okay, the expected value for this conditional state, conditional on not investing. Okay, and so I'm going to derive that in the next slide here. Okay, so this is like the conditional expectation. Okay, so the expected value is a function of the state variable and the decision. And then if you invest, well, then you have to pay the state-of-the-art cost, and then the conditional expectation of the value function is going to be conditional on investing. And then with extreme value shock, the investment probability is going to be multinomial logistic. So we just could put those deterministic parts of the value functions here into the logit formula. Just this is fully standard. And then, of course, if epsilon here is just, or eta here is 0, so that epsilon doesn't matter, this is just going to boil down to an indicator function of which value is the highest one. Okay, now the expected value functions are given by the following integral here. So here, what is this? This is the probability that firm J is investing, so your opponent. Okay, so this is an expected value for firm I. So this is a so if I is equal to 1, this is going to be J is going to be equal to 2. Okay, so firm 2. Okay, so if your opponent is investing, then you're going to get the conditional expectation given that the opponent in the next period is going to have obtained the state-of-the-art production cost. So this is why C2 here in the next period is really equal to C. Okay? And then if it's not investing, well, you're going to end up in the same state in the next period. And yet the state-of-the-art production facility marginal cost, C, that is potentially changing. And so the firms are taking expectation over how that process is evolving. So this is why we're integrating from what it is today, so it cannot change all the way down to its absorbing state C, where it's equal to 0. Okay, so So this is the expected value if there's no investment. So now if firm I is investing, well, then firm I's marginal cost of production is going to be equal to the state of the art next period. Okay, so this is why we have C1 equal to C here, and C1 just staying put at its state value here if firm I1 is not making any investment. Okay, and so here again, H, that is actually the integrated value function where you're taking the expected max over those epsilon shocks. Expected max over the two decisions, taking account for the distribution of the epsilon shock. So this is like the the Emax or the smooth max or the log sum function that we know all too well. Okay, so how do we find all these equilibria? Because it turns out that, I already talked about that there's potential many different equilibria here. So one would be like a leapfrogging equilibrium, one would be a monopoly equilibrium, and actually, since we have written into Lan's model, actually as a special case of ours, the potential also going to be a preemptive equilibrium where only one firm is doing all the investment. So how do we solve and how can we figure out is a unique equilibrium? And see, we're using this Markov perfect equilibrium concept of Maskin and Terrell that's now really widely used in empirical I/O. Okay, and that was actually meant to reduce the multiplicity that arise because there was a bunch of there were some problems with the multiplicity and focal theorem results where anything could happen in these games. So it's not tight enough structure on the problem. So they invented this Markov perfect equilibrium concept that is really widely used in I/O, and is a natural extension of dynamic programming models where you have the state variables being the payoff relevance variables as natural parts of a dynamic program. Now, okay, so how do you solve this? It turns out to actually be extremely difficult. So here's a quote from Johannes Horner in his econometric paper in 2011. It says, dynamic games are difficult to solve. In repeated games, finding some equilibrium easy, as any repetition of a stage game Nash equilibrium will do. This is not the case in stochastic games. The characterization of even the most elementary equilibria for such game, namely the stationary Markov equilibrium in which continuation strategies depend on the current state only, turns out to be often challenging. And so if like a king of game theory thinks this is difficult, I'm starting to get a little bit worried. Why I'm even teaching? Why we're teaching is why I'm even trying to solve this model. Okay, so it's really bottom line, it's pretty difficult. Okay, so how did theorists do? How do they find all these Markov perfect equilibria? So theorists, what would they do? They would guess an equilibrium and verify it. Okay, that this equilibrium can be an equilibrium. That does not seem super appealing to me. I just don't have that type of intuition. I mean, some game theorists are really, really good at theory and can guess what the equilibrium are, but I just don't have that in level of economic intuition. So I'm kind of like a computer guy that want to try to see if I can solve it. So the applied version of guess and verify is really like successive approximations. You iterate on the Player-Bellman equations. Okay, so you guess a value function, you put it in, and then you get out a new value function and say, oh no, that was not verified, right? It's like not what I put in, so it's not an equilibrium. So you put it right back, and then you do the successive approximation, and then at some point after guessing and and guessing wrong, and for some time, it's going to converge to an equilibrium, and that's kind of like the applied version of guess and verify, and then at the end you got a fixed point. Okay. So Pecos and McGuire was some of the earliest work on computing Markov perfect equilibrium. They proposed a deterministic iterative algorithm, which kind of the spirit of iterating on the Player-Bellman equations. Okay, they found a cursed dimensionality in trying to solve for the Markov perfect equilibrium in models where with firm dynamics. Even with a moderate number of firms, it turns out to be quite challenging. And then they proposed a stochastic algorithm to approximate this Markov perfect equilibrium in an attempt to to break this cursed dimensionality. But this is kind of in the spirit of this iterative algorithm where you're iterating on the Player-Bellman equations. Okay, so actually what John did after coming back from Australia was that he assigned, as a problem set, he kind of outlined this simple extension of the Bertrand price competition model to have these leapfrogging investments, and then he assigned it as a problem set for his students for the exam, and then said, okay, try to solve it using the Pate-Gist-McGuire. And then the problem was he got as many answers as he got students, okay? And this could be, of course, because all the students, didn't know, were completely clueless, or it could just be, as we found out, because there were so many different equilibria, okay? And so starting the algorithm one place gives one solution, and starting it in another place gives a different solution, okay? And so it's almost like, since different students use different starting values, they all give different results. And so this is where John and Fedor and I try to work on an algorithm that could be, guessing more in a more systematic way, okay, and then just, coming up with starting values. Okay, so our findings in this paper are really based on the computation of all the Markov perfect equilibria on this dynamic game of Bertrand price competition and leapfrogging investments. And then our ReStud paper develops this new solution approach consisting of a state recursion algorithm for finding all stage game equilibrium, and a recursive lexicographical search algorithm that finds all the combinations of potential equilibria along all the Markov equilibrium paths. So here, the problem is really the traditional solution approach does not work for models with multiplicity of equilibria. I mean, it's very intuitive, right? If you think about it, just multiple equilibria, that's like having multiple solutions to the Bellman equations. When do you use successive approximations? Well, you use it when the Bellman equation is a contraction mapping, okay? So you would like to do successive approximation until convergence, and if it's a contraction mapping, it's going to have a unique fixed point. But multiple equilibria pretty much goes against that idea of having a unique fixed point, so it can't be a contraction. Okay, so it really fails the standard time recursion because of the multiplicity of equilibria is destroying the contraction properties of the Bellman operator. And this means that you're going to get potentially different solutions for every different starting value. This means that implementation of the Bellman operator, if you say imposing symmetry or something, is acting as an equilibrium selection rule. But then also the algorithm itself, this choice of starting values, because you don't have the contraction mapping property, convergence is not guaranteed, and if it's converging, then it depends on where you started. So different starting values, different equilibrium, and it's not really like a scientific approach to just get new solutions every time different people solve a model. So that's really dangerous, and this is why we think you should try to develop algorithms that can solve for all the Markov perfect equilibrium, and then you can select among them based on economic grounds, but not based on how you initialize an algorithm. I'm going to show you actually a little bit at some of the results later here. The danger of imposing symmetry would be a natural thing to do would be say, okay, these two firms, they have the same access to the same potential technology. They're starting the same stage. They have the same discount factors, same payoff functions. Everything is like fully symmetric. We conjecture it's going to be a symmetric equilibrium. And we actually did that first and tried to solve for the using the successive approximation. But then we got something that was like a dog chasing its tail. Okay, it's like imposing the symmetry really knocks out a bunch of equilibrium. The ones that are really left, well, these are unstable symmetric mixed strategy equilibria that are extremely hard to find with the successive approximation algorithm. Okay, so let's move on and talk about the state recursion algorithm now in detail. Now we know kind of about the model, and we know that it's potentially hard to find these solutions. Okay, so here's a picture of the state space. So recall the state space is consisting of the marginal cost of production for firm 1 and firm 2, and then the state-of-the-art production technology at any given time. And then you can never have marginal cost of production that are lower than the state-of-the-art production for technology, because that's only improving over time. And how could you ever have costs that are lower than the state-of-the-art if it's never happened before? Okay, so here's an example where we discretize the states into 4 points from 0 up to 3. So you got 0, 1, 2, and 3, and then on this vertical axis you got the state-of-the-art. Okay, so down here, so this is like the last digit that the state-of-the-art. Okay, and then along this axis here, you got the firm 1, and then you got firm 2. Okay, marginal cost. Okay, so the first axis, that's a marginal cost of firm 2, and the second axis for marginal cost of firm 2, and then the vertical axis, that's the state-of-the-art cost. Okay, so this is the state space. So it looks like this pyramid. Okay. So this point out here is not possible, because then you would have like a marginal cost that would be lower than the state-of-the-art production technology at this point. Okay, so you got 333 here, but then you would have 332 here, but out here that would not be feasible. Okay. Anyway, so as C decreases, then the game fall through the layers of the pyramid in this way. So you're going to start here in the apex of the pyramid. And then the state-of-the-art technology improves, and then that makes the state space fall down through to this layer. Of course, you're going to be only in one state at a time, then depending on whether the firms have invested or not. Okay, and then the C decreases, you really fall through the layers of the pyramid like this. Okay, so let's start with that. Okay, so consider some potential transitions that are feasible, and go see how the state-of-the-art is developing. Okay, so here's a simple dynamic of game dynamics. Okay, so the game started in the apex at some point, then the technology improves, and then the state-of-the-art cost falls. So now we're in point. This is 333, so this is 332. Okay. And then say both firms are simultaneously investing. So now you're in the point 222, which is here. Okay, so this is like what we call the corner of the pyramid. Okay, it's like a corner, and these are the edges, and this is like in the interior. Now then technology improves again, and then you fall through to the interior point here. Now, nobody has invested yet. Okay, so the state-of-the-art has just improved, so now you're in this interior point. And say, then firm 1 invests to becomes the cost leader, so it's on the edge here, not in the corner where you would end if you with simultaneous investment, or if one firm is investing after another without any technology improvement. But this is the edges. Okay, so you see, you can kind of see you're moving towards this corner here in different ways. Okay, and so this is again state-of-the-art technology improves until its absorbing state. Then firm 2 leapfrogs firm 1 to become a new cost leader, and then finally firm 1 invests at the game reaches its terminal state. Now you would consider, why would he ever want to invest here? There's no strategic room for investment at all. You're not, the only thing that's going to happen here if you invest is you're going to lose the investment cost. But then this can happen if you have these highly extreme value shocks. So there can be idiosyncratic shocks to investment. But otherwise, this would probably not happen. Okay. So these are the game dynamics. So you start at the top, and then you move towards the end of the game. So this motivates us to try to solve the model. I mean, each point of the state space, there's going to be a value function, right? So the value function and the choice probabilities are defined over all these points in the state space. And when you're calculating the value function, well, you're considering the transition to the next states. And so when you're implementing the Bellman equation, well, then you need to take those multiply with the transition matrix and everything. And then you do the successive approximations over time, or try to solve it with Newton or whatnot. We're not going to do that here. we're going to do it, instead of doing time recursion, we're going to do state recursion. So, and we can do that because of the directionality of the game. See, in this game, there's no transitions away from this point, so we can start solving for the value function in this point first, and then having the solution here, then we consider states where there's only transition to that point, and then we can solve that. So this is going on here. So we solve for the terminal states, then we solve for the bottom layer edges, because there is no transitions to the interior because you can't get rid of your technology, and then once we have solved that, well, then we solve the value functions in the interior, because here there's only transitions to the edges and to the corner, but we already calculated the solutions here. It's not like your technology can suddenly get worse, so there's no transition upward in this pyramid. So then once we have the solutions here, we can then go up one layer, and then again we do the same thing. We start in the corner, then the edges, then the interior, go up one layer, then the corner, edges, interior, and then you do that all the way on until you're the apex of the game, and then solve all the sub-stages of this game. This is the simple idea of state recursion. And actually, I mean, you couldn't use state recursion for the hero circle problem, right? Because here there's a loop, because if you make an investment, you're gonna the state of the bus is regenerating to its initial value, so it's like a renewal problem. You can't use that here. You can't use it for state for the game of exit and entry that we had in the Gilligabirian mirror example from last time. That doesn't work either. Anyway, so well, once you've done the state recursion, the whole game is solved, okay? Now, all of this is actually conditional on an equilibrium selection rule, because there could be multiple stage game equilibria in each case, okay? And this is what is creating the multiplicity of the game, and this is where this recursive lexicographical search algorithm is coming into the picture. Anyway, so before we start talking about all of this, let me just give a few examples of what this state recursion can be applied to. And talk a little bit about the theory of directional dynamic games, or DDGs. Okay, now as mentioned here, as C fall through the game, it only falls, it never increases, right? And you can map these transitions here into a graph like this. Okay, so these are all the state points. So you got the bottom layer down here, the absorbing point of the state. The absorbing point of the game here, this is the corner, and you got the apex all the way up here, and then all the points, the different layers of the pyramid. These are like different stages of the game. Okay, so here I've marked this is the apex, the first, second layer with state of the art has fallen with one value, and then so it's 2. And it's 1, and it's 0 here. So this is like the bottom layer, and then you got the corner, the absorbing state. And then I've colored all these points here with the same colors as we have here. So you got corners of red, edges of blue, and then you got the interior points. Okay, so here I'm marking all the possible transitions that can happen if you're only considering the transitions happening through the state-of-the-art improving. Okay, so as C increases, the games fall through the layers of the pyramid in the following way. Okay, so these are the feasible possible transitions due to technology. Okay, of course, this means you would actually never reach the absorbing state, because if you're falling through from any of those points and just falling downwards, you can never end out here, right? In these edges. Okay, so these are examples of potential transitions that can be done due to technological progress. But there can also be strategy-specific partial ordering on the state space. So, partial ordering, I mean, the way in which the states are ordered, which state is coming before another state. Okay, those are happening before another state. It's kind of the ordering of the state. And the strategy profile induces a partial order on the state space here. And here's one particular strategy. That would be firm 1 is investing in all interior points. Okay, so every time firm 1 is an interior point, it's going to move to an edge. Okay, so the edge where it isn't doing the investment. And this is what is going on here. Firm 1 is doing these investments. These are the edges where firm 2 has invested. Okay, so this is a subset of transitions. And here's a strategy where firm 2 is investing in all the edge points, and that's how you get to the corner. Okay, now these are just examples of on possible transitions, and then here you got the other those that are the transitions induced by the technology. So if you have a combined strategy where firm 1 is investing in the interior and firm 2 is doing in the edges, these would be the possible feasible transitions. Now, of course, these are just made up strategy profiles. So we want to see, okay, what are all the possible transitions that can happen in the state space, and then figure out what the feasible transitions are. So here's the combined strategies for both firms. So this is inducing a partial ordering on the state space that looks like this. Okay, or and first this state comes, and then this one, and then you go all the way to the state. So these are the feasible strategies, are the strategies. Then these are the points that are potentially visited. Okay, now let's talk about what is a dynamic game. There's two conditions. There's the no loop condition, and then consistency of the strategy-specific partial ordering on the state space. These are the two. So you can have the following transitions. You can have self loops where you stay in a state for some time without any transitions, and then move to the next state, and then move around. Okay, but you cannot have a transition back to a state that has been visited before. Okay, so this, in other words, if you think of the game that we the state Bertrand Price competition game, well, then what you cannot have is any movement from the bottom of the pyramid and the back to the apex. Like suddenly the technology suddenly becomes old again. Like if it's computers, then suddenly the state of the art is Commodore 64. Okay, no longer like the the Mac Pro that I just got. Okay. Anyway, so you can't have the no loop the no loop condition. If you have that here, then suddenly the state of the art could go back. Well, then if there's suddenly technology improvement again, then you can like cycle forth and back between those states, and you can't have that. Okay, so this is ruled out. This is ruled out. You can't loops. Self loops are okay, but not this loop. Okay, because then if you go back to any state you visited before, then you can there's a loop here or a loop here. Okay, so you can't have that. So it's like, think of it as you can also, like you talked about the stochastic bargaining over the stochastic shrinking pie. Then if the pie is sometimes growing, then you have a loop. Okay, if it's both shrinking and growing. So then another thing is you cannot have two different strategies that induce opposite transitions. We call that inconsistent partial ordering of the states, because what in both these cases, actually the no loop condition is satisfied, right? It's not like there's no loop here. Everything here is okay, right? No loops. It's not like you can go like this, because it's not possible. The problem is these two errors are going the wrong way. But if you take the course's common refinement, or the union of those two partitions or those strategies, well, then it actually creates a possibility of a loop if you combine the two strategies. Okay, so if this happens, say, with probability 0.5 and this happens with probability 0.5, then the combined effect is that you go down here, and then sometimes, well, then you can go back to that state, right? And this creates a problem, because then you have a loop between two states. So even though conditional the strategy, there's no loop, then there can be loops, and that makes directionality fail. And it invalidates the solution approach that we're using, where we relying on the directionality to do the state recursion. So here's the definition of the directional dynamic game, or dynamic directional game, or DDG. It's a finite Markovian stochastic game where the following holds. So it's a DDG in this case. So every feasible Markovian strategy, sigma, satisfies the no-loop condition. And every pair of feasible Markovian strategies, sigma and sigma prime, induce consistent partial ordering on the state space. So in other words, this cannot happen. Okay, so you can't have sigma and sigma prime inducing different partial orders of the state space, or arrows pointing in opposite directions. Okay, so here's the strategy independent partial ordering on the state space, which is like the closest common refining of all partial orders induced by all the strategies played by that are potential played by the players. Okay, so here's all the orders here, and you see there's no loops, and there's one absorbing state, and in fact this is what we call a directed acyclic graph, or DAG, because there's no loops and it's a directed graph. And here's an absorbing state, and here's where we start. So all the arrows essentially pointing that direction. So how do we then solve it? We solve it by DAG recursion, by starting with the terminal state. So what we do is we partition the state space into several stages identified by the terminal state. So here's the terminal state, the absorbing state. There's only arrows pointing to this direction. And once that's identified, we remove it. But then once that's removed, there's a new set of terminal states. Terminal states are states where there's only transitions to these states, but not away from them, except from the now removed terminal state. Okay, so this is like the edges at the lower level. Okay, so at the absorbing state for the marginal cost of production, but where none of the firms, where only one of the firms have done the investment. Now, so you identify those terminal states. That's another stage of the game. Okay, and then you remove the terminal states. You identify new terminal states, and that is the next stage of the game. Okay, so now you can see here. See, there's only, since there's no arrows pointing away from here, we can start solving this game here, and then we can solve these stages here, and all this stuff can be done independently. And then once you got that, then you can solve this. So you solve backwards. Okay, so then you kind of follow this process here again. You identify the states and remove them, and then you just go the whole 9 yards all the way to the tapping. So now the stages. They may be that the states are partially ordered, but the stages are totally ordered. Okay, in the sense that this becomes these edges come before the terminal states. All of them are before. Okay, so everything is ordered. It's totally ordered. Okay, whereas these states here are partially ordered. Okay, so it's not clear that this is coming before that one, for instance, right? Because they're just different places at the edges where you can arrive depending on the realization of strategies and technology improvements. Okay, so the total order of the set of the stages also defines subgames of the directional dynamic games that follow all these different stages, and you can solve those subgames one by one. So we're going to do that by backward recursion. Okay, so here's the state recursion algorithm. Once you have identified all the stages of the game, you can start doing the state recursion. So first you solve for the last stage, it's absorbing state. Having solved that, then you move on and solve the next stage and backwards, and then you just move up and solve stage by stage. And note, when you're solving a stage, let's go back to this one here. All these points here are at the same stage. They can be solved independently. So if you have a large problem, you can solve that in parallel. But you would have to solve this, each of the stages, in a recursive way. So in serial. So there's no room for parallelization there. But yeah. So yeah, that's just. Since it's a recursive algorithm, it's that part. That part of that recursion is evidently it has to be done in serial. Okay. So state recursion versus backward induction. I mean, you could think of this as being backward induction on the state space rather than through time. Okay, so so it's, in a way, it's a generalized way of backward induction. If you have a finite horizon model, well, it's going to be actually totally ordered in a directional game, because time is directional, right? So you think of time as being the state that's ordering all the states. Okay? Now, but our algorithm is running on state space instead of time period. So states does not have to be time period, but it could be like the combination of the cost states as in the leapfrogging game. Time also evolves deterministically, right? It does not have to move deterministically from state to state every period for this to work. Okay, you can have the self loop. That's what we talked about, right? So you can work with stages for transitions that are stochastic, not necessarily happening in a deterministic sequence. Okay, like time. Okay, so the states does not have to be ordered in the same deterministic way as in time. Yet, with probability of going above against the direction, well, that has to be 0, right? So it has to be directional. With the multiplicity, state recursion is performed conditional on a particular equilibrium selection rule. Okay, so we haven't talked about multiplicity yet. Right now, we just said everywhere here there is one solution, but imagine there's several solutions, several value functions that solve this stage game equilibrium here in this particular stage point. Well, then there's different ways you can go to the absorbing state, right? I mean, maybe one equilibrium is that firm 1 is doing the investment. Maybe another equilibrium is that firm 2 is doing potential investment in this point. Okay, and then these arrows would go in opposite directions. Okay. Anyway, so these are the possible this we need to take account for. Okay, so so here's what happens. Okay, so now we know actually in the absorbing state there's a unique equilibrium. We know also at the edges there's also a unique equilibrium, and if there's no epsilon shocks, it is do not invest. But in the interior, where none of the firms have yet invested, there could be several equilibria. In the lowest layer, that could be 3. And so what do we do in order to work with that? And then up here, we don't know how many equilibria there are, and that depends on actually further equilibrium selection down here, because when you calculate the value function here, well, it depends on what equilibrium was selected there. So you can still do the state recursion, but you would have to make it conditional on an equilibrium being selected in a given point in the state space. Okay, so this is what the RLS is doing. It's basically taking all the combinations of equilibrium selections that and calculating them in a very systemized way. Okay, that we have an algorithm to do it. Okay, so here's the building blocks of the RLS algorithm. So the stage recursion algorithm is solving the game conditional on the equilibrium selection rule, and then RLS is efficiently cycling through all feasible equilibrium selection rules. Okay, like all the combinations of if it's equilibrium number 1, 2, or 3, that through the state space. Okay. Now the challenge here is that the choice of a particular Markov perfect equilibrium at any stage game at any stage may alter the set and even the number of stage game equilibria at earlier stages. Okay, so it's not like we can say all interior points have 5 equilibria and all corner states have 1, and we could show that up front, because depending on which equilibrium was found or the selected further down the pyramid, it can affect the selection of equilibria at higher stages. Okay, so we need an algorithm that can actually deal with that. Okay, so here's back to this graph we talked about before, like the which one of the 3 equilibria that you select here actually can determine whether there's a unique equilibrium here or not. So say it may be different number of equilibria depending on whether you choose an equilibrium where firm 1 is investing with a high probability or firm 2 is investing with a high probability, or vice versa. Okay. So that is something that we see. Now let's see what can happen in some of these stage games here in the interior points. So you can have several different types of best response functions, and here's some examples. So sometimes you have a unique equilibrium where none of the firms want to invest. So it's, obviously if the marginal cost of or the cost of investment to achieve the new marginal cost of production is just prohibitively high, so nobody would ever want to invest regardless of whether there's competitors or not. Well, then that could be an equilibrium, right? So you see that that depends on parameters, of course, how often that happens. Okay. But if they're not prohibitively high, well, then there could be potentially investments. And so here's various combinations, and you see here the anti-coordination structure of the game. One where firm 1 is investing with probability 1 and firm 2 is not investing, so they want to invest at the same time. And then one where it's flipped around, where it's firm 2 is investing with probability 1, and then a mixed strategy. Okay. But there can also be other type of equilibrium patterns. Here there's 2 mixed strategies and a pure one, or 4 mixed strategies and a pure. Okay, and these are feasible equilibrium stage game equilibria that we encounter through this game. So you can see now, if this can happen, this type of equilibrium can happen, different types of equilibrium can happen at this point, where either there's no investment, or firm 1 is doing the investment, or firm 2 is doing the investment, or there's mixed strategy, or there's several different mixed strategies. Well, then and that potentially affects which equilibrium is affected up here. Then it started, if you combine all these different combinations and the size of the game is big, then there's going to be quite a lot of different combinations of what can happen. And this is essentially also what happens. Anyway, so in order to systematically cycle through all these different equilibria, we create something that we call the equilibrium string of digits here, okay? And that has the following property. That so what we do is, any point in the state space, well, we number them, like in this example here, we have numbered the stages, the state points, one being the apex, and then the absorbing state having the highest number. Okay, so you got this equilibrium state string of digits. This is like the absorbing state, and then you got the apex here. This is where you start. In this case, we have like a case with 14 stage points. So the state of the art can take values c equal to 0, 1, and 2. And then all their combinations with the C1 and C2, where this state of the art are always better than or at least as good as what the C1 and C2 are. Okay. Now then we can, and for each of the stage points, well, then we can assign an equilibrium number. Okay. So this is what we are doing. Okay. Now any of these points in the state space may depend on points to the left, higher digits, and not a point on the right. Okay, so they need to be partially ordered and obeying the total order in the stages. Okay, so here you got stage, essentially the first stage that was solved for. Then you get the next stage here. Then you got the interior points. There's another stage, and there's another stage here, and then another stage, and then this interior stage here. Okay, so just like you have before. So this is just a way of basically numbering the equilibrium string of digits. Okay. Okay, so there's an equilibrium string of digits with as many digits as stage points. Okay. So what it is it's a number that gives an instruction of what number of equilibrium to look for. So we use base 0 indexing. So 0 means look at the first equilibrium you find. 1 means look at the second equilibrium that you find. So just like you would do in Python and C. Okay. And so if there's several equilibria, and suppose you take all combinations of C of equilibrium numbers, if there could be, let's say, 3 equilibria at each of these points, in each stage points, well, then you need all the combinations, right? And that's a complete lexicographical order of equilibrium selection rules in a base 3 number system. Okay, so here's take the first equilibrium that you find, then you in all stages. Here's taking the second equilibrium in the apex. Okay, and it's take the third equilibrium in the apex, but actually none of these are actually feasible. Anyway, and then you move on, and then you see this is like the number of combinations in base 3 number system with 14 digits is going to be 4.7 million numbers in this lexicographical order. So that's quite a lot of combinations, even if you just had 3 equilibria. I mean, we've seen examples where there could be 5, so then the number is going to be even bigger. And so searching through all those combinations of 1, 2, and 3, or 0, 1, and 2, is going to be extremely demanding. Okay, and especially if you have a high-dimensional state space. I mean, here our example, we discretized the state-of-the-art cost into only 3 values: 0, 1, and 2. Okay, that's not really a big game, right? And I mean, it could be. So how do you deal with that? Okay, so it turns out that many of those equilibria are not even feasible. I mean, there's many points of the state space where it's just never optimal to do any investment, for instance, or where you would always want to invest. Okay, where there's a unique equilibrium, and particularly at the edges and in the corners, it's always going to be a unique equilibrium. So there's no reason to actually consider all the points in the partial order. So this is where we if you follow this picture that you have here, you don't need to cover all the cases. Okay, so let's take one by one. So you start first with taking the equilibrium string of digits, which is corresponding to 0. Okay, so like the first number in the number system, and then you calculate the number of stage game equilibria when you are taking the first equilibrium all the way through in the state recursion. Now, then having calculated that and calculated the value function all the way through, then you move on to the next one. But then you realize that there was only one equilibrium here in the first in the top of the pyramid. Okay, it's there was only one equilibrium. Okay, in all here in the apex. Okay, so so this is not a feasible equilibrium selection string. So you can just jump over it, and you can jump over the next one. But then this one is admissible, and then you solve the game. Okay, and you move to the second equilibrium in this point of the state space that could be potentially 2. Okay, so now once you have chosen a new equilibrium selection rule here, corresponding to the points in the state space you're making transitions to have changed, then you need to recalculate the solution in this point in the apex, right? Because there's transitions to something where you're picking another solution. So you need to recalculate that. But there's no changes in the rest of the game, right? Because these are transitions that are happening after this point. Okay, and these solutions have not changed. Okay. So this is really something that is speeding up the algorithm, that whenever you're choosing a new equilibrium selection rule, you don't have to do the whole state recursion. Only change the calculation in the states where that's actually been a potential change. So we only resolve in this one point, not in the entire state space. And then you just go from there and look at only the feasible equilibrium selection string. So here's kind of what's going on is you're jumping over huge blocks of infeasible equilibrium strings, and so well, you can once you have jumped over and calculated the first equilibrium and then recalculated here, you take the next three equilibrium, you jump right over those two infeasible equilibrium selection strings. And then you make jumps all the way down here, because in this entire area there's only a unique equilibrium. So all these equilibrium selection strings are just infeasible, and then the next one is down here where you can move to the next equilibrium selection string. Okay, so you can see how this is kind of systematically going on. Now, what it's doing here is really that instead of using the base number system, where the base is 3 for all the digits, we are actually using a variable base arithmetics. So we are using a number system where the bases of the numbers are different. And actually, here the base is 1, so because there's one equilibrium, and here it's 3, and then there's 1 and 1 and 1. Okay, so it's like it's different bases. So it's like it's the binary number system, the hexadecimal number system, and the decimal system. They all have different bases, right? But they all have the same bases at each of the digits. This is not what we're using here. We are using variable base arithmetics, not the fixed base at all, the same base at all the bases, but a variable base. Okay, so here's an example. So let 3, 1, and 2 be the bases of 3 digits, and then allow the digits and the numbers for the allowed digits are the numbers 0, 1, and 2 for the first, when you have base 3, right, like we've seen before, and then there's the base 1, then the only thing is feasible, that's 0, and then base 2, that will be 0 and 1, like binary numbers that you all know too well, right? And then so this is going to be for the first one, for the variable base, for the first digit, for the first digit, and then for the second it's 1, and so on. And then what happens is when you add 1, well, then you add 1 to the last digit. Okay, now there was 2 digits, so you can have 0 and 1. Okay, if you add 1 after that, well, then you have to add to the next digit, but that's only one possibility, right? So you move all the way up to the next digit again. And so now you are 101, and then you add 1 again, and you can see the mechanics here, but it's not actually that crazy hard. But you can see here what is really going on here is that we're adding 1 in variable base arithmetics where the digits are equal to the number of stage game equilibria. So this is all what RLS is. So you just need to recompute the number of equilibria at each stage of the game, and then do variable base arithmetics, and then just add 1. So how simple can that be? I mean, it's you just essentially have to add 1 in a little bit funny number system, but add 1, and then you got the next equilibrium selection rule. And that's really what RLS is. That's all what it is. So you start with the equilibrium selection string. You start at 0, very natural. Then you run the state recursion using the current equilibrium selection rule, formalized by this equilibrium string of digits, which is currently 0. Then you save the number of equilibrium in every stage game as the number of equilibria for a given equilibrium selection rule. Then, like I said, you just add 1 in that number system to obtain a new feasible equilibrium selection rule. Now, so add 1, that is, then you have a new equilibrium selection rule, which if you go back here, adding 1 in this number system, well, that was, since there's no feasible, adding 1 when this digit has only one feasible number, named as 0, that it needs to use the next digit, and then the next feasible one is by adding 1 to this number. So this is all what is going on. Okay, so the stopping rule here is that the successive function, like adding 1, exceeds the maximum number in the number system given the number of digits. So you stop if that's the case. So if you run out of digits, that means you have done a complete full enumeration. Like, if you go back here, that corresponds to going through all the digits in the partial order. Of course, not in this number system, but in the number system with the variable bases equal to the number of equilibria at each stage game. Okay, and then so you are not stopping. Then you go back to do state recursion using the equilibrium selection string. Then you update the number of equilibria, and then you update what needs to be resolved, like the points in the state space where they could be potentially have been changed. And then you add one in this number system, and then you go from there. Just to you just loop all the way until the successive function is done. This is really like a tree traversal algorithm or on the stage game. And now here, recall what is 14. 14 is the absorbing state, and then there's basically different ways to get to the absorbing state depending on what equilibrium selection was taken. Okay, so you can say it's really like a tree that branches, and then it branches at each of the state points into different branches. So here you basically you start from where you have we start from the absorbing state, and then you move on through the states, and then at some point here there would be potential 3 different equilibria you can follow. Okay, and the idea is you go all the way to the end where there can be changes, and then you do equilibrium the branching there. Okay, so you go all the way to the depth of the tree, and then where there's a potential branching, well, then you just take them one by one. Okay, so you but record at each of these points that there could be potential multiple number of equilibria. Okay, and then you just visit all the different branches. So once you've covered all the 3 digits or the 3 equilibrium selection rules at this point, well, then you go all the way back here. Then you continue this path, and then you go through all the state space all the way to the top, and then you redo the branching there. And so see here, there was, say, this equilibrium selection actually knocked out the possibility of 3 equilibria at this point. So this is all happening endogenously, but RLS does not care a lot about this, because its number of equilibria is just recalculated every time that you are updating the solution, so that at the points in the state space that needs to be updated, not in this part down here that's just reused all the time. And then you just essentially just go from there and just enumerate all the different equilibria in this very systematic way. And the way to do it is just by a combination of variable-based arithmetics and then adding 1. Okay, that's what really RLS is doing. Okay, so the main result of the RLS algorithm is really a decomposition theorem. Okay, so we assume that there exists an algorithm that can find all these Markov perfect equilibria in each of the stage games. So this corresponds, we need an algorithm that can find the solution to, find the fixed points of all these things here. Now, in our game, we can actually solve these analytically when eta is equal to 0, when there's no extreme value shocks, and these are some solutions to polynomial equations and a little bit of combinatorics, very easy to calculate. Okay, but in the more general case, we would need to an algorithm. But see that the type of algorithm that you need to find to solve for this is much simpler than finding the overall solution to the entire game. I mean, this is a simple 2-dimensional problem. Here you can do it grid search if you want it, or you can do like a combination of successive approximations and bracketing to trace out all these different equilibria. Okay, so I mean, essentially you are just searching over a 2-dimensional space here, and repeatedly, instead of just searching over a high-dimensional space determined by all the different states and all the different players and all the different actions simultaneously. So this is one of what our main result is. Okay, you have this decomposition theorem. So assume that there's really exists an algorithm that can find all the Markov perfect equilibria at each of the stage, which is not so hard to do, at least not as hard as finding the overall solution. Then that number of equilibrium is and that number is finite. Okay, otherwise it would be hard to find all the solutions if it's infinite. Then RLS finds all Markov perfect equilibria of the dynamic directional game, of the overall directional in a finite number of steps. So it's equal to the number of total number of Markov-perfect equilibria. So in other words, while it is an iterative algorithm, the number of steps is equal to the number of solutions. So every time you do a step, you find a solution. So no successive approximations that need to converge. It's just computing the equilibria. Okay, so that is this is from our ReStud paper. So then there's a weaker version of it, basically saying that that it can at least find one equilibria in each of the stage game. Then it can enumerate some of the equilibria. Okay, which sometimes is better than nothing. It's not like if you fail to find one equilibrium, it's not like it's screwing up finding any equilibrium. Okay, so here's some examples and some running times, and what I have just for comparison show here is the upper bound of the number of equilibria if you were using a number system with a base equal to k equal to 3. Okay, which would actually be wrong because would be wrong to do because in some cases there are actually 5 stage game equilibria, so it had to be even larger. But just with 3, so what are the number of combinations? You've already seen the 4.7 million combinations when n was equal to 3. Okay, in the lexicographical order. Okay, that was the many different numbers in the lexicographical order that I outlined here. Okay, now of course if k is bigger, so you have to count to 3 before you jump to the next one, or 4 and jump to the next one, then it's going to be even bigger. If there's more digits or more states, it's going to be even bigger. Okay, so n here, this was n equal to 3, but there's more states, it's going to be then of course there's going to be more digits, and then the numbers is going to be even bigger. So here, if you have n equal to 4, so like 4 different values as a state-of-the-art cost, then there's going to be many more states, and the number of the number of combinations in the lexicographical order, well, the equilibrium string of digits would be about 4 billion combinations. Okay, and now if you have then the upper bound of the number of equilibria when n was equal to 5, that would be 174 septillion different combinations to look for equilibria, which is like totally out of the blue to look for, right? So how much time does it take to solve this model? With we ran try to solve the leapfrogging game. Simultaneous move with n equal to 3. In this case, there's actually only 127 feasible equilibrium selection rules, and which is equal to the actual number of Markov-perfect equilibria in that game. So only 127 out of almost 5 million combinations, and it took only 0.08 seconds. Of course, when big numbers, the game is bigger, then it takes longer, so it's 46,000 equilibria in that case, and it takes 0.3 seconds to enumerate and calculate the value functions of all these 46,000 equilibria. In this case, with n is equal to 5, well, then you found here for this parameterization 192 million equilibria. Okay, that's quite a lot. Okay, and actually, we also for n equal to 5, we try to calculate equilibria where we found even more than this number, like about 1.5 billion equilibria. Of course, this takes too much time, and if it's for better or worse, what it shows is that this model has a huge amount of multiplicity that gives some potential concerns with the applicability or usability of game theory in this context. I mean, how can the two firms with so many different combinations even think about coordinating on any of those 192 million equilibria? Anyway. Now, this is a simultaneous move case, okay? Now, in the alternating move case, under certain sets of parameter values, that could be there's sometimes a unique equilibrium, or there's often many fewer equilibria in the simultaneous move case. In the simultaneous move case, even if there was, if we were to do the case where the upper bound or in the lexicographical order with k equal to 3, would be the 174 septillion combinations in the lexicographical order. There's only one equilibrium, so it's going to find it right away and know where that is stopped because it's running out of digits right away. Okay, so that took 0.06 seconds. Okay, so RLS is really, really powerful to solve also models that has unique equilibria, because then it's going to be very fast, and it's also going to be able to know that it is a unique equilibrium. So it can find out, compute, if it stops and find only one equilibrium, then it means that there's only one equilibrium. It's not that you don't really know if it's just because you have this starting value that you found this solution. You know that there's only one equilibrium, which is really nice to have. And of course, if there's fewer equilibria, it's more feasible. Okay, so let's look at the solution for the leapfrogging game. There's a bunch of theorems, and I'm going to try to keep it brief. One of the things that we find is there could be either 1, 3, or 5 Markov perfect equilibrium in the simultaneous move stage games when eta is equal to 3. We show that there exists a non-iterative algorithm that finds all Markov perfect equilibria, and it's like based on the solution of some polynomial equations. Okay, so that's one of the things. Then they find in the another theorem shows in this alternating move case, well, there can be only 1 of 3 Markov perfect equilibria in the game, so not 5 in each of the stage games. This automatically just limits the number of potential equilibria that there can be. Okay, compared to the to the simultaneous move formulation of the game. So actually, we generally find fewer equilibria in the simultaneous move game. And here we also have a surefire way to find these stage game equilibria. Okay, so here's again the best response functions, and this is what we can solve for pretty much analytically in this case. But even if you don't have an analytical solution to this, this is much easier to find solution to games like this compared to finding the solution to the overall game. Okay, now let's revisit some of the results about the resolution to the Bertrand investment paradox. Okay, so we got the earlier work by Freudenberg and Reichenau and Freudenberg and Tirol about the investment paradox. We're going to focus on here the Riordan and Salant results about preemption and rent dissipation, where there's a unique equilibrium. Okay, which is a unique equilibrium. Now, preemption, that is, only one firm is aggressively investing, completely dissipating all the profits, just to keep the other guy out of the market, and then the other guy is not investing at all. Okay. Now, that's what Riordan and Salant show is a unique equilibrium. This is the only thing that the model can predict. Okay, their model is with a continuous time and continuously improving state-of-the-art technology. We show that this is really a nice result, and the predominant type of equilibrium does not involve a preemption and rent dissipation. We find many types of endogenous coordination that can happen in equilibrium. Most of them involve leapfrogging, some sort of leapfrogging, but we can also get preemption or duplicative investments. Duplicative investments is it's already happening here with this mixed strategy equilibrium. So with some probability, there's a positive probability that both of the firms are investing at the same time. Okay, so that can also happen. That was totally ruled out in Riordan and Salant. Okay, so and this is the situation that the defense in the Australian cardboard case would say this cannot happen, right? If the firms can end in this situation, this bad situation where they simultaneously investing, why would they ever want to do it? Well, it is an equilibrium because they potentially they can happen probabilistically in a mixed strategy. Okay. So, and it's also an equilibrium that one firm is investing and another firm is not investing. So many different things can happen in this model. Now, these equilibria are generally inefficient due to overinvestment. This is one other finding that we see. So actually, we see the opposite of what the defense claimed, The defense claimed that the predominant equilibrium would be nobody would ever want to invest in this market if there was Bertrand price competition. We find that the opposite is the case, that generally in the vast majority of the cases there's going to be inefficiently many investments because of competition. The competition in this market is inducing overinvestment. Okay, the fact that there's two firms makes them to invest too much to leapfrog each other and compete for the customers. So we find these duplicative and excessively frequent in investments as an equilibrium outcome. So this is really the solution to the Bertrand investment paradox. No investment by both firms cannot be an equilibrium, Markov perfect equilibrium outcome if it's not prohibitively expensive to invest. So in other words, if it's socially optimal to invest in any state point, then not investing by either of the firms cannot be an equilibrium outcome. So I mean, that none of the firms are investing with both firms are investing with probability 0 cannot be an equilibrium outcome in the simultaneous move formulation of the game. So that's really just right there the resolution to the Bertrand investment paradox. And that's just not happening. Okay, so we got the multiplicity of equilibrium. So here's a theorem. We can prove that the sufficient condition for uniqueness in the alternating move version of the game is that generally in this game is that the firms are moving in alternating fashion, and has to be not simultaneously. And then for each C in the support of the the state-of-the-art transition probability, we have that it's not possible to stay in the same state. Okay, so the technology is always moving, except from in the absorbing state, of course. Okay, now this means that technology is just deterministically moving every period. Maybe you don't know how much, but you know that it's never staying put. This means that you're never staying in the same state, and this means that if the two firms are alternating their moves, it means that they're never in any way in the same state again. Okay. Okay. So if this is happening, then if firms are then you have a sufficient conditions for uniqueness. So this alternation and complete foresight or certainty that you're not staying in the same state creates sufficient conditions for uniqueness. It's really like possible to ravel up all the way to the future that you know when you have your investment possibility really. Okay, so but on the other hand, if firms move simultaneously, equilibrium is generally not unique. If technological change is stochastic, that is, if there's a possibility that no change is happening, then equilibrium is generally not unique. And is what is really creating the simultaneous? What is really creating the multiplicity of equilibria is it's a simultaneity in the choices in choices between the two firms, and that simultaneity can actually happen in the alternating move case as well if the states are not moving, because then with some probability you're going to return to the same state, and it's like you're staying in for some time in a state, and that's a little bit like having a simultaneous move game. So that it's a simultaneity in this anti-coordination game that creates all this multiplicity, and that's why if you have alternating move case without any with potential having potential being allowed to be in the same state, then you have the simultaneity as well there, and that breaks the uniqueness, and then you got multiplicity of equilibria. Okay, so now here's the multiplicity of the equilibria, the number of equilibria in the simultaneous move game. Well, if investment is socially optimal, then the support of the Markov process for the state-of-the-art cost is the full interval. Well, so you have like a continuum of states. Well, then you have a continuum of Markov perfect equilibria. So it's like a full theorem results, like anything can happen. Okay. Okay, so it's not like anything can happen. but there's a continuum of things that can happen. Okay, because we show that the payoff matrix or the payoff map for the simultaneous move game is a triangle with vertices that are basically the origin. So now the payoff map, you're thinking about the value function in a particular state, say the apex of the game. And then the points are really the origin where none of the firms are getting any profits, so value functions are both zero, and then the monopoly profits for either firm 2 or firm 1. Okay, and then VM here is that's expected value, expected discounted payoffs in the situation where it's firm I is the only one that has the right to move and is really acting as a monopoly investor. Okay, now that's the ideal situation for a firm. You get to decide when to invest, and you never have to worry about the other guy investing. That's a monopoly solution. So you can see if anything can happen in this convex hull between those three vertices in this triangle, it's like, if everything in here can happen, well, it's like all the extremes, both the complete rent dissipation outcome with zero profits, and then the monopoly outputs where firm 1 is getting all getting all the monopoly surplus, or firm 2 is getting it. Then it's like a little bit like a full theorem result. Okay, so you got these payoffs. This is a case of deterministic progress, but once you have stochastic technological progress, then you start to fill out this triangle, and so here each point denotes an equilibrium, okay, at different points. So you got value function for firm 1, value function for firm 2. Okay, you see each point here corresponds to an equilibrium, and in some combinations, many different equilibria results in many different combinations, right? So yes, so up here, there's many equilibria that actually result in this potentially monopoly outcome. Okay, whereas there's fewer here each. So the size of this dot determines the number of equilibria that has that exact combination of values in this apex point. And then you see if your stochastic technological progress, then all these different equilibria is kind of filling out the triangle. You get more combinations of value functions. Now in the alternating move game, well, you got basically that the convex hull of the expected discounted equilibrium payoffs at the apex is a strict triangle of this triangle that you got from the simultaneous move game. And you can see here. So here's an example. I think here we got the simultaneous move game. Here we have how many do we have? 28 million different equilibria. I'm getting blind. So this is like thousands. You got 28 million equilibria. And then over here with the same set of parameters, but just with essentially alternating moves and get a simultaneous move, you get much fewer equilibria, only 17,000. I mean, this is definitely more feasible to solve, right? It's going to solve much faster, and so working with alternating moves or even stochastic alternating moves is going to make models easier to solve too. Okay. Now here, what you can do is when you calculate all the different Markov perfect equilibrium, you can calculate the distribution of them and look at the distribution of various outcomes that are associated with each equilibrium. Say the efficiency of the equilibrium. So you can calculate consumer surplus and producer surplus, and calculate the total surplus. Both for the social planner situation and for the duopoly decentralized outcome, and then compare. Okay, so here 1 corresponds to get the maximum surplus that the social planner would get, and then 0 that would be no surplus. Okay, so the complete rent dissipation equilibrium that you get out of Switzerland, that would be like efficiency measure of 0. But we don't get an efficiency measure of 0. Actually, most of the equilibrium that you see for this particular equilibrium distribution, if you call it a distribution of efficiency across all the equilibria, is mostly efficient. Okay, the simultaneous move formulation of the same game is less efficient, right? Because it creates this simultaneity that generates a possibility of inadvertently actually trying having duplicative investments due to, for instance, the mixed strategy equilibrium. And this is also something you really can see here. Like here's a distribution of all equilibrium. There's a mass point here at 1, so there's actually like quite a lot of the equilibria that are fully efficient. Okay. These are all the pure strategy equilibria, because if you plot the distribution of the mixed strategy equilibria, you see that they are in the simultaneous move game that none of them are actually efficient. It's not it's hitting 1 from above, right? So it's not like coming from below here. Okay, so it's there's no efficient mixed strategy equilibrium, and it kind of goes against the idea of making a duplicative investment for 2 firms producing the same good, and that's just inefficient, right? So so that's the kind of stuff you can compute, and see you got yeah. So that's a theorem saying that a necessary condition for the strong pricing games is that you pay pure strategy equilibrium only if you want to have efficient equilibrium. This is what you see out here, right? Okay, so here's the Reardon-Salant theorem. It says that in error formulation of the model, it means that the state-of-the-art cost not prohibitively high, and you got almost continuous but deterministic technological progress. In that case, you have a unique market perfect equilibrium. You got preemptive investments and full rent dissipation, and this we can generate with our model. So here you got a simulation from the model. You got the state of the art. It's just ever improving here. You would discretize the state space into quite a number of different points. I can't do the counting, probably something like 50 or something. So like a quite big state space, right? So like 50, 50, 50 for all the different values, of course, and limited by the shape of the pyramid, but potentially many. And then what you see here is that it's the blue one here. That's the marginal cost of production for the monopolist or a social planner monopolist, right? So this is when it's optimal to invest. Okay, so these dates here's an investment. Okay, then the marginal cost of production and the prices is falling. Okay, now in this equilibrium, you see it's only firm 2 that's doing any investment. Okay, firm 1 is not doing any investment at all, and firm 2 is doing so much more frequent compared to firm to the monopolist. So you got over investment, and actually if you calculate the profits in this case, they're going to be 0. Okay, so you got full preemption and full rent dissipation that can be created when you put the high investment cost and low marginal and discretize a lot, which corresponding to like very short time periods, and it's a little bit like working towards a continuous time limit. Okay, but you can have under investment, but most likely most of the time you have over investments. Here's an example that shows the preemption is not really a general equilibrium outcome. So these are results from the from this alternating move case. So even in that case, you can have leapfrogging. Okay, so it's not a general outcome. It's a feature of those very specific assumptions about deterministic technological progress and deterministic alternation of the game. Okay. If you have if that's not the case, if you don't have continuous time, then you can have leapfrogging. Okay, and this is a little bit like, there's some time where there's more room for actually making simultaneous, or there's more room for getting a short-term monopoly power if your turn where you can have the low cost, where we can take the advantage of being a cost leader is longer. It's like a little bit like nature is doing the coordination for you. Okay, then you can have leapfrogging. Okay, leapfrogging here means the first one, firm 2 is investing, then firm 1, then firm 2, then firm 1, then firm 2. They take alternating and doing the investments. If you have a random alternation, well, so that it's random who is taking the turn to move, then you can also have leapfrogging. Okay, which is kind of making a lot of sense. If you have a random one-step technology, so it's not, you see here now the technology is not moving, regularly every time, but sometimes it's just not moving. It's it's random when it's moving. Then it's just impossible for the preempting firm to plan ahead of doing preemptive investments, because it can risk that it just not getting the right to move when it should have invested, and then the other firm is investing, and then it's possible to preempt. So in that sense, in that respect, Riedel and Celan's result is not robust either to random one-step technology. It says there needs to be that. If there's drastic changes investment, well, with alternating moves, well, then you're going to get leapfrogging as well. Well, why not take the opportunity if suddenly you're the only one that has a right to move and there's a drastic change in technology? Well, then you're gonna pick up on it and leapfrog your opponent. This is also what we see. Simultaneous move. This is what Riedel and Celan conjecture that their definition of the game or the equilibrium would still the result would still hold with simultaneous move game. That's not the case either. Okay, so you got leapfrogging just the minute just a second you change the model to have simultaneous moves. And, okay, there are many other types of investment dynamics, but leapfrogging is one of them. Here's an illustration of what happens when you ignore if you impose symmetry of the equilibrium, which is a very appealing assumption, right? If symmetric payoff functions, and start the same point of the state space, all these things that are symmetric for those two players. The whole thing is symmetrically described. Same discount factor, same cost functions. Everything is symmetric. Why not impose a symmetric equilibrium? Well, what we have done here is we have marked the equilibria that are in fact symmetric. Okay, these are the equilibria down here, and recall this is the triangle with all the equilibrium payoffs, where you got the value of firm 1 here, value of firm 2, or the other way around, and you see this all the inefficient mixed strategy equilibriums. Symmetric equilibria that are down here. These are the inefficient one that involves the symmetric mixed strategy equilibria. So these are in fact a very, very specific selection of equilibria that is chosen in a little bit arbitrary way of symmetry that you think is an artifact of having symmetric solutions. But in this anti-coordination game, you pretty much rule out many of the combinations of leapfrogging that are happening. Well, of course, if you have a mixed strategy, then there's a potential for both duplicative investments and leapfrogging because the investment probability is random. But you knock out basically all the pure strategy leapfrogging equilibria that do exist. Okay, so yes, it's all these different solutions, and you can see I can't see how many equilibria there are there. There's is there like 164 million equilibria, and only very few of them are mixed strategy. I don't know how many, but not a lot. Okay. So, how do you find all these? Could we use? We're using the recursive lexicographical search algorithm, but what about a homotopy approach, where you're using path-following algorithms, and then you find some homotopy parameter where you can find a solution for one parameterization of the model, and then gradually change that parameter and follow the path of the solution just by making small steps and following using a path following algorithm to do the homotopy approach. And this is something that has been suggested in the literature as a full solution approach for solving dynamic games. So here's what happens if eta, the scale factor of the I extreme value term, if that goes to infinity, it's like flipping a coin, right? It's only that there's no strategic room for investments. You determine your entire your entire behavior in the market is going to be determined by extreme value shocks. Everything else doesn't matter, right? This means you just 50-50, you're going to miss that best. Of course, in cases where you where it's not exactly infinity but smaller, then it's gonna smooth out the best response functions that you have for the deterministic case. Okay, and this you can see here. It's kind of as you increase eta, things becomes more and more smooth, and then the equilibrium is then changing more and more. And then the question is, could you follow the path of those equilibria and see and then see and use some path following algorithm? Of course, you would need to change it more slowly, but you can see it's like here, this equilibrium here is moving from here and here to here, right? But then all of a sudden, this equilibrium is potentially disappearing, so it's not going to be, maybe it's not straightforward. But this would be like a natural equilibrium homotopy parameter, because you can create a situation where you find a unique equilibrium, and then you just follow all the purifications along the path of changing eta. So the idea with the homotopy parameter is simply just to start at high value and then with a unique equilibrium, and then change eta gradually, and then trace out all the multiple equilibria by following all the bifurcations of the path of the equilibrium selection. The problem here is that's quite many purifications if you have 1.5 or 192 million equilibria. It's just too many purifications along the path to use a homotopy approach. And in the equilibrium correspondence is not even all hemicontinuous if you look at it. So here's one equilibrium correspondence for the alternating move case, where you plotted the value functions for player one for not investing in the top of the point. So this there's a graph for each point in the state space, but that can't show that, so I'm just show one point in the state space. And then see as you have eta very high, well then value is unique. There's unique equilibrium, but then at some point here, then the equilibrium bifurcates, but it's not. You have to go all the way up here and back in order to trace out these three equilibria. So now suddenly you have three equilibria, which corresponds to like 1 point in the state space. You suddenly have three equilibria, and these are like separated. Okay, so it's really hard to trace out. Okay, now and you can see this is already the beginning, and now it's only getting worse once you look at all these different solutions. I mean, here at this point where eta is equal to 0, this is where you probably have something like millions of equilibria. Okay, whereas you're only one here. So just forget about homotopy for solving this game. It's just not feasible. Okay, so let's try to see a video of what's going on, and as see the payoff map, how it changes if we change eta. So you can see here we start with eta around 0.5, and then we're going to decrease it all the way until we are at 0. So here's this right now a unique equilibrium, but then eventually this is going to be, so we are resolving, now it's falling, so that two more equilibria pops up, and then it's like you can see they like popping up out of the blue. How can you even try to follow the path of these funny shapes of equilibria as eta is varying? Okay, so you get this funny psychological or psychedelic picture, like if you've taken too much LSD, and you got all these funny pictures. Anyway, so this is just a recorded video where we just saw all these different equilibria for many different values, and then recorded that, and try to follow all these paths. That seems like pretty hard to do. Okay, Anyway, so this is maybe not recommended. So here's the conclusion for the Patron investment model. Because we find many types of endogenous coordination that's possible in equilibrium. We find leapfrogging, we find preemption, we find duplicative investments, which happens when there's simultaneous investments. If the full anticipation and monopoly outcome is actually supported as a Markov perfect equilibrium. So this corresponds to the corners in the triangle. But you can also get essentially a complete rent dissipation and zero profits for both of the firms. And so then this convex hull of this triangle is really like everything can happen. So it's like a numerous multiplicity of equilibrium that fills out the triangle, and we get like folk theorem-like results. If you work with continuous states, then it is the entire triangle. Okay, and so this is really pointing to a huge inefficiency, and the equilibria that we find is generally inefficient due to overinvestment, due to duplicative and excessively frequent investment, which pretty much goes against the idea that the defense had in the collusion case, that why would firms ever want to invest in B9 if they're Patron price competitors? In fact, this is what they get out of this type of competition. So John was right in the collusion case, and even though he was not able to solve the model, or his students were not able to solve the model the first time, his original intuition was right. B9 would have reduced the prices, and so the damage was definitely not zero, and certainly not in the long run. Okay. Now, solution of dynamic games are really hard when you have so many equilibria. But we have an equilibrium solution, a solution that deals with that, the recursive lexicographical search. But when the equilibrium is not unique, the computational algorithm inadvertently can act as an equilibrium selection mechanism if you're using the standard approach of successive approximations, right? Like every Bellman equation with different the Bellman equation should produce only one result, right? If there's it should produce all the equilibria that you're looking for in a not ad hoc way that's determined by how you initialize the algorithm. So, but when there's directionality in the state space, well, we have an algorithm that can be formalized by state recursion and do that over time iteration. This, in combination with the recursive lexicographical search that is based on this idea of variable-based arithmetics with adding 1 to trace out all the equilibria, that is guaranteed to find all the Markov perfect equilibria of this particular class of games if you have good algorithms to solve for these very simple stage games. One of the findings that we find here is that this huge plethora of Markov perfect equilibria really poses new challenges. This is kind of the deep thoughts coming out of this. Starting to become a little bit philosophical here. Is how firms can really manage to coordinate on a particular equilibrium. It's like hundreds of millions of equilibria, even in this highly stylized and highly discretized, coarsely discretized model. And this also potentially increased difficulties of empirical application. Okay, because if so many different things can happen, it's almost like there's no structure put in the model. It actually turns out that this huge multiplicity of equilibria is really not necessarily a big problem for identification. It does give some less structure, but actually, even in the case with like millions of equilibria, we're able to identify the right equilibrium selection mechanism if you have enough data in the Monte Carlo experiments we have been running. Okay, but it does generally give daunting perspective for identification of the equilibrium selection rules from the data, especially if those equilibria can be different at different markets, and so how do you define that? How do you identify that equilibrium selection rule if there's like so many things, so many different equilibria that can be selected? So in order to estimate the model with the with a nested approach, what we can do is what I'll cover shortly, the nested recursive lexicographical search algorithm, where the recursive lexicographical search algorithm is used. It's a nested algorithm inside a hill climbing algorithm that searches over the parameter space. There's more to it. It's not just a repetition that fully solves for all the Markov perfect equilibria and maximizes over them. That maximization is done in a very efficient way using mixed integer algorithms called branch and bounds, and you can really rely here on a lot on the data and rule out a lot of low likelihood branches on the tree. So anyway, I'm going to talk more about that in the next lecture. For now, I just want to end with a little video and some nice music from the Neil Young album "Rust Never Sleeps." So today, yeah, bye bye, or what should I say? Hey hey, my, rock and roll will never die.